All right, so here on page 11, we're going to start calculating some heat. And there are two different equations we're going to be looking at, and the first one that you see here is the Q equals mH equation. This does actually apply to chemical changes and some phase changes. When we have like water boiling, it's changing from a liquid to a gas. That's what we were talking about with phase changes. And these are a little bit different from each other. This whole unit we've been talking about chemical changes and chemical reactions. And so here when we start changing into some physical changes, just water boiling, it's still water, it's no chemicals changing, no bonds being formed or broken. There is a little bit of a difference in what we're going to be seeing happen here. And so I want to talk about it here at the top of the page where you have that sign convention. We've been talking about like endothermic reactions having a positive delta H, where heat's being absorbed. And then negative delta H's mean it's exothermic. And these are true for chemical reactions as well as our physical changes where things are boiling. We take water, liquid water, and add heat into it, and that's an endothermic process to get that liquid to turn into a gas. We have to add heat into it. But there's a difference in what we observe from the outside, from the surroundings when this is happening. In our chemical change, when we add heat into a reaction, because that chemical change is using that heat energy to break bonds, energy is kind of getting used up. And so it's feeling colder because the heat we're putting into that reaction is not heat anymore. It's getting turned into a potential energy, a stored energy where we can't feel it. Kept talking to you about batteries. Take energy, electrical energy, and put it into chemical energy. It doesn't get hotter even though that battery has more energy. It's not thermal energy. It's a different type of energy that we can't feel. In phase changes, like with that boiling example I was talking about, if we add heat into that liquid water to turn it into steam, that steam, that gas, is going to feel hotter, feel warmer than the liquid is. And so that energy is being used, yes, but it's still kinetic energy, it's still thermal energy that we can feel. So both of these are endothermic processes, but in the chemical reaction, like what we've been focused on most of this unit, we're not going to feel that heat after it gets used up and kind of tied up in those bonds. And in a phase change, with a physical change, we still do kind of feel that heat. So keep that in mind as we're talking about this. That's not going to be the focus of these notes, but a lot of times once we start kind of switching gears here to physical changes, which is going to be the focus of our page, is the physical changes, the phase changes. It's the same equation when we talk about reactions. Then don't get this kind of too twisted up in your head. So focusing on these phase changes and this first equation that we can use to calculate the heat of these phase changes. First off, this Q is heat. That's what it represents. H normally as a variable is height, but then our capital H is our enthalpy, or heat of vaporization word. So the heat energy is measured by Q. And then of course M, like we've seen it before, represents mass. Keep in mind that that's always going to have the units of grams on it. And then that H thing that I have highlighted in pink here is either going to be the heat of fusion or the heat of vaporization. And these are slightly different. It really comes down to what type of phase change is happening. Like it says here for our heat of fusion, that's going to always be used when something is melting. If I have a solid, I need to add in a certain amount of energy to turn it into a liquid. But it also does apply when something is freezing, just the opposite of melting. So melting or freezing, we're going to use the HF, the heat of fusion value there, as our H. And the heat of vaporization is when something is boiling or vaporizing. Also, if it is condensing, the opposite of vaporizing. It's going to be the same value, the HV value here. And notice that even though these are both values, H values for water, they are different values. And what this tells us with having a bigger heat of vaporization for our water than the heat of fusion is it takes more energy to cause our liquid water to turn into a gas than it does to turn our solid into a liquid. Keep in mind, this is the energy required to melt a gram or a mole of a specific substance. So the bigger the value, the more heat it causes or requires to change. So if we do our first calculation here, this is asking us to calculate the heat required to condense 5 grams of steam at 100 degrees Celsius to water at 100 degrees Celsius. So keep in mind, this temperature is not changing, and so we can ignore those temperatures. Later on, we're going to see some temperature changing, and so that's going to require us to use a completely different equation. So if we notice the temperature is not changing, that just means we get to use this normal Q equals mH equation. And we're trying to calculate heat, and we need to multiply the mass times the H value, and the mass is sitting there right in our problem, that's 5, and we just need to choose the right H value to go with it. And I've kept that heat of fusion and heat of vaporization for water up at the top of my screen because this is water, steam, so we're going to need one of those values. The thing we need to focus on here is which value do we need. And because we are condensing here, which is the opposite of vaporizing, but now we're going to be using the heat of vaporization. Like we said, we're turning our gas into a liquid, and that's going to release this much heat. So we're going to use that 226. I'm not sure why that's a 0 over here, because the standard number is 2264. My bad. Just using our standard heat of vaporization number, and all we've got to do is multiply those. It's going to be a big number, but 11320 is our final answer. That is technically the unrounded answer because we should be rounding this down to 3 sig figs, and we really try not to give you big numbers like this to round down this much, but 3 sig fig answer would be 11300, replacing that 2, which would be a 4th sig fig there, with a 0. Keep in mind, we can write these zeros here. If there's 5 digits, there's only 3 sig figs unless we put a decimal at the end. That would make it 5 sig figs. So 11300. Now I know we're used to our heat, our energy being measured in kilojoules, but if you notice, these H values that we have here are all regular old joules. So this is going to be regular old joules on our final answer. Let's look at the next one, where we're not going to be calculating heat. We're going to be calculating the mass of CCl2F2. And so we can use that same equation. Once again, when there's nothing about a temperature change happening, so we're going to use our original Q equals mH equation. This time, though, it gave me the heat, the energy that is being absorbed, as well as the HV value, which I do want you to go ahead and cross out moles there, change that to grams so we can use it to find those grams like we want. The only other kind of twist that we have here is that notice how this energy is in kilojoules. We need it to be in joules to match the joules energy that we have in that HV value. So if we remember that kilo means 1,000, 1 kilojoule is 1,000 joules. That means that this 500 kilojoules is going to be 500,000 joules. So that's what we're going to be plugging in to our equation. 500,000 joules is equal to some mass of our chemical times the HV value that they gave us. And at this point, if we've just plugged in the numbers to this equation, then we need to divide by whatever number is with the thing we're looking for, dividing by the 21, so that by the end we can have M all by itself on the same side, or on one side without anything else there with it. And our final answer ends up being 23809. Let's make that a little bit clearer. 809. There's a lot of other decimals there. We don't need this many sig figs, but that is going to need to be 3 sig figs again. So 23800. And keep in mind, mass is measured in grams. Now, some of you might prefer to rearrange this equation where we do that opposite over neighbors. So if we were solving for M equals the opposite side of the equation over M's neighbors. And we still end up doing Q divided by H, still end up doing that 500,000 divided by the 21. You just didn't have to do any algebra to get those there. You just plug them in to that equation. Either way, we get the same answer, and I do not mind whichever way you choose to work this out algebraically, as long as we can all agree on that final answer. This next question asks us not to do a calculation, but if we put 3 unknown substances, X, Y, and Z, on the same source with equal masses. So the mass and the energy they're getting is the same. They're asking which one would melt first and last. And because everything else is the same except for these H values that they have, and remember that these H values represent the amount of energy required to get these substances to melt, whichever one has the smallest amount of energy required is going to melt first, because it requires the least amount of energy to make it change phase. And that means that the largest value, that Y value, is going to be the one that melts last, because if everything else is the same, it needs almost more than 3 times as much energy to make the same change as element Z did. So at the bottom of the page, we get to talk about temperature changes. And this equation is very similar. We still see that Q there representing our heat. We still have M there for mass, and this time we have this delta T, this triangle T at the end. Keep in mind, just like triangle H, delta H is measuring the change in energy throughout our reaction. The delta T is the change in temperature throughout this process. So we're always going to be subtracting to find how much that temperature changes. And a lot like our stoichiometry, we really don't care about the sign, whether we're adding or removing heat, whether it's going up or down. So just subtract the larger temperature minus the smaller one, because if we always plug in positive values, we're never going to be wrong about these answers. And I'll talk to you more about that in class if you're concerned about those signs. But for our class in this situation, it doesn't really matter. So the only thing that's really new here is the specific heat, that C value. And that's basically like the H value we were seeing up at the top of the page. C, that specific heat, is a measure of how much energy it takes to make a change happen. Except this time the change we're observing happening is that temperature change. So keep in mind that this is an intensive property. And just as a general review, this is the same number for the same substance, no matter how much or how little we have. It does not change when we have more or less of a substance. And just like we were talking about with those XYZ chemicals, if we have a small C value, a small specific heat, if we give it the same amount of energy as something with a larger specific heat, this one is going to have a larger change in temperature, because it takes less energy to cause this substance with a low specific heat capacity to change temperature. Something with a higher specific heat capacity needs more energy added to it to make it change temperature. So if we put these two objects on the same heating source with the same mass at the same amount of time, then we would notice the one with the lower C having a bigger change in temperature and the bigger C having a smaller change in temperature. Now, that C for water is a constant. It's not something you need to memorize, but we are going to need it in a couple of these problems. So I'll put it at the top of the page when we need it. And the other C's you're going to be seeing in your podcast for homework on page 12. So first question asks us to calculate heat, which means we get to just plug in all the numbers we need to this Q equation. And to calculate this Q, we're just going to take that mass, the M, times the C for our substance, which is water. So we're using that 4.184 number just from right above this problem. And then our delta T, our change in temperature here, if I'm going from 10 to 80, is going to be 70 degrees Celsius. We're just subtracting those two numbers. And this heat is going to be 219,660, which if we do round to 3 sig figs like we should, you might think, okay, 3 sig figs, 6 rounds the 9 up, that would be 220,000, 220,000. But unfortunately, because of that rounding, none of those zeros at the end are significant. So there are a couple of ways we can fix that. The simplest is to put a line over this 0. We're never going to give you something like that where you need to memorize or remember to use a line to make one out of all those zeros significant. And some people think that means that the zeros go on forever when you put a line over a number. So the other way to put this in 3 sig figs without making it kind of weird, although I know as students you don't necessarily want scientific notation, but that is the best way to do this scientifically. So 2.20 times 10 to the 5th, and then of course this is going to be joules because our C value is just plain old joules here. So that would be the best answer that we can get here definitely need to round that original answer there. So, as always, we can calculate heat with this equation, but we can also calculate other values. We can rearrange this equation or just plug in what we know and solve for the missing value. So this one is asking us to find the specific heat capacity of some unknown element. So we're going to be solving for C here. It's up to you whether you're going to plug it in like I do, or if you want to rearrange the equation. Remember, opposite over neighbors, if we're solving for C, is going to be Q over M and delta T. And the most important thing to do, if you're remembering to do it this way, is to multiply those together first and either do it separately and combine them, multiply them before you do anything else, or when you plug it into your calculator with everything else, put it in parentheses. Otherwise, this answer will not turn out to match my answer. So I'm just going to plug in these numbers that we see in the equation. The heat that is released by this substance is 20.4. The mass that they gave us is 10. C is what we're solving for. And since I was going from 42 to 35, my temperature was changing by 7 degrees. Your math teacher, if you're looking at an equation like this, would probably tell you to combine like terms, combine those numbers that are on the same side. So leaving the 20.4 the same, 10 times 7 is 70. And then we still have the C there. And in order to solve for C, we'd need to divide by the number that is on the same side. So we're dividing by that 70. So 20.4 divided by 70, which is the same thing we would have been doing here. Taking our energy divided by the quantity of the mass times that temperature change. And we get that our C value should be 0.29142. And rounding that down to 2 sig figs would be 0.29. Now, the units for C are kind of crazy, but just like I gave you that specific heat for water that has these units on them up top, I'm going to give you lots of other specific heats on the test, and you'll see them like on page 12 as well in a table format, and it tells you what the units are for specific heat. So just focus on matching them. Technically, this is the same thing as what we were doing with the numbers over here. Q was measured in joules, our mass was measured in grams, and our change in temperature is degrees Celsius. So really, we're just kind of putting all those units together in the same format as we put our numbers together as well. So they look complicated, but it's really kind of simple. And then we've got one more question on this page. And this one has a couple of different things going on, including some kilojoules that we need to deal with, just like we dealt with them at the top of the page. So keep in mind that because 1 kilojoule is 1,000 joules, if I have 9.75 kilojoules, that's going to be 9750. We multiply by 1,000 to remove that decimal 3 times to the right to get our joules out. And here we're trying to find mass. So we're going to be solving for M. If you like rearranging your equation first, then that's going to be Q over C times delta T. And just like in the last problem, make sure you multiply that C and delta T together first, or put parentheses around it in your calculator. If we just plug numbers into this equation, though, we can get to that same answer. We're still dealing with water, so that is going to be that 4.184 number that I brought down. And if we're going from 35 to 45, then our temperature change is 10. My process here would be to combine like terms on that other side. So I'm going to actually multiply that 4.184 times 10, which is 41.84. And then to solve for my final answer, I need to divide by the number that is with the thing I'm looking for, dividing by the thing keep in the way of me saying M equals something. So my final answer is going to be whatever that 9750 number is divided by 41.84. And that ends up being 233.03. 3 sig figs is what we want to keep because we have a 3 sig fig number here and here. So our mass is going to be 233 grams, of course. I hope that wasn't too bad. It is some simple equations, and you will be given these equations. You don't have to memorize them. The most complicated thing is trying to choose between which equation you're going to need for any given problem. So your homework podcast tonight is going to use these equations to help do a little bit of calorimetry stuff on page 12. You don't have to worry about page 13 for now. We'll have a little bit of time in class next time to work on that.